let's begin. So we had seen some basic formula of differentiation last time, that differentiation of x to the power n is given by this formula where n can be any real number. Okay. Differentiation of any constant is 0. Okay. Differentiation of a linear function is nothing but the slope of the linear function. Okay. Differentiation of a constant multiplied by a function becomes constant times differentiation of that function. And differentiation as of the sum or difference of two functions is equal to the sum or difference of the individual differentiations. So these are the properties of differentiation that we had discussed apart from the basic formula. Okay. And of course, we had seen the definition of what differentiation does. It gives us the instantaneous rate of change. For a function, the differentiation gives us the instantaneous rate of change. So these were some of the ideas that we discussed in the last lecture. So let's look at some examples from worksheet number 2. So I'll start with a couple of things from question number 1. Let's look at, for example, part C. So y is cube root of x. Okay, so we can write differentiation of y with respect to x as differentiation of cube root of x. So that can also be expressed as differentiation of x to the power 1 by 3. So now using this particular formula, differentiation of x to the power n, this becomes n into x to the power n minus 1. So this is itself the correct answer, but we can simplify this further and write this as this, or even this. Okay. So any of these will be sufficient to express the correct answer. Yes. Similarly, coming to the last part of this question, y was some kind of a cubic function. So here when we express differentiation of y with respect to x, substitute this cubic function. And now we can make use of the combination of these two properties here and further express it as differentiation of x cube minus, take the constant 2 outside. So differentiation of x plus differentiation of 6, but this is a constant, so anyway that derivative will be 0. So this is 3x square by the x to the power n formula. This is 1. Differentiation of x will be 1, and differentiation of the constant 6 will be 0. So finally the value becomes 3x square minus 2. Okay, let's quickly discuss about the second question, which is like an example of an application of the concepts of differentiation in solving a problem based on straight line motion. Okay. So we have that situation that two vehicles start from the same x coordinate at t equal to 0. Okay. Moving along this, but they move according to the given equation that A's distance covered, which will be the same thing as displacement, as a function of time is 8t square, whereas B's displacement as a function of time or distance is equal to 4t cube. Distance and displacement will be same here because it's motion along a straight line, okay, without changing direction. So from this now we can also see we have some extra information. We have the information that A's instantaneous velocity will be given by the instantaneous rate of change of A's position with respect to time or displacement with respect to time. So that will be 16t. So A's instantaneous velocity as a function of time is 16t. And similarly, B's instantaneous velocity as a function of time is differentiation of this function 4t cube. So B's instantaneous velocity becomes 12t square. So additionally, we can derive these two informations from this. Okay. So for example, what we can understand is that suppose we check at time t equal to 1 second. Okay. What is happening? A and B's positions are 8 meters and 4 meters. So you can see that definitely A is ahead of B. And also we can see that A and B's velocities are 16 meters per second and 12 meters per second. So A is faster. A is moving faster. Okay. So if we were to check this diagram, we would see that at t equal to 1 second, if A is somewhere here, correspondingly B is somewhere behind. And if A is having a velocity like this of 16, this one is having a comparatively smaller velocity. Okay. But by the time we come to, for example, 2 seconds, we can see that A's displacement is given by 8 into 2 square, so 32 meters. And incidentally, B's displacement, which is given by 4 into 2 cubes, is also 32 meters. So they have come alongside. Okay. So at t equal to 2 seconds, they are right side by side. But we can also check that their individual velocities at this moment are 16 into 2, that is 32 meters per second, and 12 into 4, that is 48 meters per second. So at this stage, we can see that B is faster. So you can see that A's velocity is 32, but at this stage, B's velocity is more. So B is in the process of overtaking right now. So that is why what we'll also see is that by the time we come to let's say t equal to 3 seconds, you can see that E's displacement will be far behind B's displacement. E's displacement will be, for example, 8 into 3 square, so that is 72 meters, and B's displacement will be 4 into 3 cube, so that is 4 into 27, so that is 108 meters, I believe. Okay, so by the time we come to t equal to 3 seconds, B is further ahead. And that we understood why is that's the case, because already at 2 seconds they are overtaking. B is overtaking A, and of course B's velocity will also continue to be more. So you can see at 3 seconds A's velocity will be 48 meters per second, whereas B's velocity would have increased quite a bit more to 108 meters per second. So B will continue to run ahead of A after 2 seconds because B's velocity will be greater. So above is a visual representation of what we are observing for these three particular instants. Okay. So for example, if you want to find...
Sir, I have a doubt.
Yes.
How did you calculate the distance covered by A and B at t is equal to 3 seconds?
At t equal to
3 seconds.
3 seconds. Okay.
Yeah.
So let's substitute in this formula. SA is equal to 8t square. So that is 8 into 3 square. So that's 72 meters. Got it, no?
Okay, sir.
And similarly for B also, just put it in the formula 4t cube. No?
Yeah.
So now, for example, if we want to find the instant at which B overtakes A. So what we have to see is that B's displacement should just become equal to A at that instant, so that B's displacement becomes greater than A's after that. Okay, so just substitute for this condition that B's displacement greater than equal to A's displacement happens for what condition? It happens for the condition that 12t square, 4t cube should be greater than 8t square. Or in other words, 4t cube minus 8t square should be greater than equal to 0 after B overtakes A. So if we take 4t square common, we have t minus 2. Okay, so this shows us that t is greater than equal to 2 for the displacement of B to become greater than equal to the displacement of A. So that means at the instant t equal to 2 seconds, B is overtaking A. Something that we've seen in the diagram also, because we observed particularly what was happening at 2 seconds in the diagram also. But suppose we had not analyzed this point of 2 seconds before, even in that case, by just solving this condition, that the condition for B to overtake A is that B's displacement from that instant onwards should become greater than A's. So greater than equal to gives us the condition that B is overtaking at that particular instant. Whereas, for example, we can also see that at t equal to 1 second, A is faster than B. Okay, but at a later time, like t equal to 2 seconds, B is faster. So that means there must be some time in between 1 and 2 seconds when B's speed becomes more than A's speed. So we want to solve that. We have to solve for the condition that VB should become greater than VA. So that will give us the instant at which B's speed becomes more than A's speed, or B starts moving faster than A. So next up, we want to find the instant of time at which P starts moving faster than A. So for that to happen, this is what should happen. So substituting from above, 12t square should become greater than equal to 16t. Okay, so that is why 1.33 seconds will be the instant when B starts moving faster than Okay. Now let's come to some of the parts of the fourth question. The third question is fairly straightforward. You have to just follow the instructions of the question, and I have given quite detailed solution. So you can go through it once more. Okay. Question 4. Let's look at this part, D part first. So y is given by this rather lengthy looking expression. So when we have to differentiate y, it just involves solving a bit of algebra before we differentiate. Okay. So what we can do is, before we come to dy by dx, we can simplify this. Simplify it by just separating out the terms. So we can write this as x square root x by 2x minus x cube by 2x first. Okay. And then further we can simplify it as 1 by 2 into x to the power 2 plus half minus 1 minus 1 by 2 into x to the power 3 minus 1. So that will make it this. Okay. And then it is fairly simpler to differentiate. So once we've done this simplification, you can just directly apply the formula now. Okay, so this type of question is just a matter of patiently applying algebra. Let's look at the E part also next. So we have this type of a function 5x, x square plus 5x plus 2. We want to find this. So first let's simplify this. So this will become x square into root x plus 5x into root x plus 2 root x. So this is x to the power 5 by 2 plus 5x to the power 3 by 2 plus 2 root x. This is our y. So now derivative or differentiation. Just involves these kind of steps now. Sorry, 3 by 2. Which we can then further simplify and write like this. So this or this, both of them are correct answers for the rate of change finally. And we can always take LCM and further simplify it also, but
Sir,
yes,
sir, I had a doubt in the B part of the question.
in the B part of this one,
Yes, sir. The B part of the uh,
fourth question.
yeah.
Yeah, so in that what you do is you just expand this. So y is x square plus 1 whole square. So just expand this. Okay. So it's x to the power 4 plus 2x square plus 1, right? And now you differentiate.
Okay, sir.
So, so differentiation of x to the power 4 will become 4x cube, right? Then differentiation of 2x square will become 2 into 2x, that's 4. And differentiation of 1 is a constant, so it's 0. So we are left with 4x cube plus 4x.
Okay, sir. Thank you,
Okay,
sir.
and you can factorize this also, but either of these is enough. Okay.
Yes.
Okay, now the fifth question was one which required slightly inverted kind of thinking. Okay, that you are given the rate of change, and from that you have to construct what the function is. So you are given that y is a polynomial function of x. Okay, and dy by dx is this sort of quadratic function. Okay. So first of all, what we can conclude from this? What we can conclude from this is, if y is some sort of a polynomial, it's of this type. Okay, let's say we don't know what the degree of it is, so it's going right up to x to the power n. So when we differentiate this, we can see that the derivative will be like this. Okay. So that means if the function has degree n, then its derivative or its differentiation has a degree of n minus 1. So here what is given to us is that the rate of change has a degree of 2, it's quadratic. So what does that mean? That means that the function y is having degree 3, or it's a cubic function. So if that is the case, let us assume it's got some coefficient of x cube, which is p, let's say, some coefficient of x square, which is q, some coefficient of x, which is r, and some constant. So this is our assumption. This is the function. Okay. So the moment we say this is the function, we can see that by differentiating it, we should get this type of function. Should get a quadratic function like this. Okay. So compare this with this. So we understand that A should be the quantity 3p, B should be the quantity 2q, and C should be the quantity r. So we have assumed the function to be having coefficients of x cube, x square, and x like this. Okay, how we know that it's a degree 3 polynomial? Because it's given to us that this is quadratic. This is given. So therefore we conclude that y must be cubic. If it is cubic, let's assume it's some cubic function like this, where p, q, r, and s are constants. So what is the relationship between them and the given constants? This is the relationship, that E must be equal to 3p, B must be equal to 2q, and C must be equal to r. Okay. Now, in addition to this, some more information is given to us. It is given to us that y is equal to 0 for x equal to 0. Given that y is equal to 6 for x equal to 1. It is given that y is equal to, what else is given? Some 2 more conditions are given, right? Just go back to the question. Yeah, y is equal to 0 again for x equal to -1. And also given that dy by dx is equal to 2, or the instantaneous rate of change is 2 for x equal to 0. So each of these conditions we will put in the equations. Okay. So let us say this is our equation 1. And this is our equation 2. Where of course this is A, this is B, C. So let's put this in equation 1. So what we'll get, that y should be 0 when x is equal to 0. That means s is equal to 0. Okay. Let's just put this again in equation 1. Okay, so y should be 6 when x should be equal to 1. So p plus q plus r, s is already 0, should be equal to 6. Okay. And again, let's substitute this also in equation 1. So y should be 0 when x is -1. So that is this. Okay. And let us substitute this in equation 2, because that is the one to do with the rate of change. Okay. So substitute dy by dx as 2 when x is 0. So that means the right hand side is r, or that's the same thing as c. So now from these equations, let's see what we are getting. We are getting s is equal to 0 directly. We are getting r is equal to 2, which also means that c is equal to 2, because we can see that r's value is equal to c's value. Okay. We are also getting p plus q plus r is equal to 6. Okay. Which means that p plus q plus 2 is equal to 6. And we are also getting that minus p plus q minus r is equal to 0, which means minus p plus q minus 2 is equal to 0. So now we can solve these two equations by just adding them. So we can see 2q is equal to 6, which means that q is equal to 3, which also means that b, which is equal to 2q, should become 6. And it also means that P plus Q plus R is equal to 6. So that means P is equal to 1, which also means that A is equal to 3. So we got all the values we require now from this. We have got A is equal to 3, B is equal to 6, C is equal to 2. Okay, and we've got the function y is equal to x cube plus 3x square plus 2x. So all this information we have. So this is that slightly more manipulation type of question, manipulation based question, where we are given some information which we have to basically work backwards on. We are given rate of change of the function as a quadratic function, and we are given certain values. So because the rate of change is quadratic, we can assume that the function is cubic, and then we can set the values which are given and solve for the unknown quantities. Okay, so hope this method of solving was clear to all of you. Okay.
Yes, sir.
Okay, so some of these type of questions will take a bit of practice, okay, and might take a bit of time for you to try and work things out. Bit of trial and error might be involved, so that's why the assignments have less number of questions, but it will take you time. You have to put aside some time for solving them. Okay, and I will keep sending you hints so that even if you're not able to solve them completely yourself, but with the hints you can try working them out. Okay, and with more and more experience in solving problems, you should get it correct. Yeah, Bhavika and others, just to make the point, for I think the part 4E, there was a small error in the solution which I had sent. I had forgotten a factor of 2 or something. So just take the answer from what I've done today in class. Okay. All right. Now let's move ahead. So first of all, we will see something related to the notation that we use for differentiation. So for a given function y equal to fx, when we find out the instantaneous rate of change by differentiating this function, we also sometimes write it in short form as f prime x. So f prime x is the shorthand notation for differentiation of fx. Okay. So f prime x is called the differentiation of the function fx with respect to x, or it can also alternatively called the derivative. Derivative of the function means the differentiation, okay, of fx, which is the same thing as the instantaneous rate of change. Okay. And the other thing is, we also know that as far as the graph is concerned, the slope of the tangent at any point, let's say x equal to a, suppose, is the value of the derivative at that point. Okay. So for example, if we have the function x cube, then slope of the tangent at x equal to 2, for example. So for that, we'll see that the function is x cube. So the derivative of the function, or what we can write as f prime x, is 3x square. So accordingly, the slope of the tangent at x equal to 2 or whatever will be the value of this function at x equal to 2. By value, I don't mean the mod, I just mean whatever the numerical value of this function is, the derivative is. So in fact, let's write it like this. It will be the value of the derivative, that is f prime, at x equal to 2. So that is nothing but 3x square, substituting the value of x as 2. So that is nothing but 12. So 12 is the slope of the tangent at the point x equal to 2. Okay, so this is again interpretation of what is meant by derivative, what is meant by instantaneous rate of change, and how it is related to the quantity slope of tangent. Okay. So there's nothing really new here apart from the fact that we are using the shorthand notation for derivative of a function or rate of the change of the function as f prime if the function is f. Okay. So the function can be named by some other symbol also. So for example, if we have y is equal to g of x, then dy by dx, which is differentiation of this function g of x, can be written in short form as g prime x. Okay. Or if we have a function of some other variables like z is, let's say, some function of time t, so then rate of change of z with respect to t will be differentiation of this function h with respect to t, which in short form we can write as h prime of t. So all these notations are basically the same thing, just using different symbols. So the shorthand notation becomes important because it helps us express equations in a less lengthy manner, in a more convenient manner. The type of equations we'll be seeing today when we study more properties and more formulae. Okay, now additionally, we have some formulae for the non-algebraic type of functions. So coming back to more formulae for differentiation. So first of all, we will look at the basic trigonometric functions, which I'm sure you're familiar with from trigonometry by now. The functions itself, they are so for the function sine x, the formula of the rate of change or the derivative is cos x. So this statement we can read like this, that the derivative of the function sine x is cos x. And derivative is an alternate term for rate of change, instantaneous rate of change.
So y is equal to sine x, right?
Yeah, if y is equal to sine x, so there's another way we can express it, that if y is equal to sine x, then dy by dx, the instantaneous rate of change is cos x, because the derivative of the function sine x is given by cos x. Okay. Of course, there's a proof of this formula from the fundamental definition of instantaneous rate of change, the limit definition also. But the proof of this will not be done over here because it's not of concern for us in basic calculus. The proofs of these formulae you will be studying in advanced calculus when you come back to calculus in maths in 12th. However, if you want to venture into the proof yourself, it is not too difficult. You have to just use some properties of trigonometric functions along with the limit definition. Okay. But just for brevity, I'm not getting into the proofs here because we really don't need it at all. In physics, what is important for us is to be able to do the differentiation based on the formulae. Okay. So now similarly for the function cos x, the derivative is given by the formula differentiation of cos x is minus sin x. So this is one fundamental trigonometric functions differentiation. This is another fundamental trigonometric functions differentiation. Okay. So for example, now if we have a function which is y is equal to 2 sin x plus cos x, and we want to find dy by dx, okay, and the slope of the tangent at, let's say, x equal to pi by 6, which is the same thing as 30 degrees. Okay, so we can see that differentiation will be differentiation of 2 sin x plus cos x. So we just use the properties the way we had done before. But when it comes to differentiating, now we'll use these new formulae, which we have just learnt above. So next step, this will become 2 cos x minus sin x. So this is the derivative of the function. This is dy by dx. So if we are denoting this function as fx, then this is nothing but f prime x. And so accordingly, the slope of the tangent at x equal to pi by 6 is nothing but f prime of pi by 6. That is the value of dy by dx at pi by 6. Okay. So it is 2 cos pi by 6 minus sine pi by 6. So you know that cos pi by 6 is root 3 by 2 and sine pi by 6 is half. So it is root 3 minus half, or approximately 1.73 minus 0.5. So this is the slope of the tangent. Okay, so this is how you would implement the above formulae in a given trigonometric function. Okay, now the other fundamental trigonometric functions, let's look at their derivatives. So the remaining formula for trigonometric functions, derivative of tan x is sec square x. Okay. Derivative of cosec x is minus cosec x into cot x. Okay. Derivative of sec x is sec x into tan x. And the derivative of cot x is equal to minus cosec square x. Okay. You'll find all these formulae in a table in your module, and you can just note down the formulae in your own notes later. So you don't really have to sit and mug up these formulae. Just have these formulae handy while you're solving questions. And with practice, you will see that you will automatically remember the fundamental ones. Out of these 6 formulae, the important ones for us, the most important ones in physics are the first two, sine and cos. Those are the ones we'll see most often in future chapters in physics. Okay. Now also let us look at the interpretation of derivative of sine x and cos x in terms of their graphs. So if we consider the function y equal to sine x, for example, so we've just seen that the derivative of the function is nothing but cos x. So let's interpret this information in terms of the standard graph of sine x, which I'm sure all of you are aware of from your trigonometry lessons in maths thus far. So we just look at the graph of sine x for a limited set of values of x from 0 to, let's say, 2 pi, one cycle. So you know that the graph is, generally speaking, shaped something like this. Reaches a peak, then comes back to 0, then goes to a dip kind of point, and then comes back to 0. So it's like a wave. It's like a single wavelength of a wave. And the completion of the cycle happens at 2 pi. Half cycle is at pi. 3/4 of cycle and quarter of a cycle. Okay. So you know that pi by 2 corresponds to 90 degrees. Like this. Okay. And you also know that these values, it reaches the peak value of +1, and then it reaches the dip value of -1. Okay. Now let's also observe some other in-between points. Like for example, let us look at the point pi by 3. Okay. So pi by 3 is the same thing as 60 degrees. So you can see that at x equal to pi by 3, okay, if the function is sine x, okay, this is the graph of y is equal to sine x, then the derivative of the function is cos of pi by 3, which is half. Okay, so that means at x equal to pi by 3, the slope of tangent is equal to half, or 0.5. So the information this tells us that if I draw tangent at this point, at this point, if I draw a tangent line, that tangent line should have a slope of 0.5. Okay. But similarly, if I were to compare this with the point pi by 2 or 90 degrees, f prime x at that point would be cos pi by 2, which is 0. So the slope of the tangent at 90 degrees should be 0. So that also you can interpret in the graph, that at the 90-degree point, which is here, if I draw the tangent, it's a horizontal line. So the slope of the tangent is 0. Similarly, if you draw a tangent at, let's say, x equal to 3 pi by 4 or 135 degrees, the slope will be cos of 3 pi by 4, which you know is minus 1 by root 2. So that is approximately minus 0.7. So 3 pi by 4 would be somewhere here, let's say. So if I draw a tangent at this point, you can see it's having a negative slope. Okay. So this is the interpretation of the graph in terms of slope of tangent also. Just make a note of this.
So cos 135 degrees is equal to minus cos 45, right?
Yes. Okay. As you know, for the second quadrant, okay, we have the formula when theta is greater than 90 but less than 180, or theta is greater than pi by 2 but less than pi, we can write cos theta as minus cos pi minus theta. Okay. So for example, cos 3 pi by 4 becomes minus cos pi by 4, which is minus 1 by 1. Okay. Similarly, if you were to look at, let's say, at the point, let's take some point in the fourth quadrant. Okay. So let's take this point, 7 pi by 8. Okay. So that is 315 degrees. So the derivative of the function would be cos 7 pi by 8. So that would actually be plus cos pi by 8. Because fourth quadrant cos is positive. So it would be plus 1 by root 2 or plus 0.7. So you can see that at this point, if I draw the tangent, it's having a positive slope. Okay. But at the same time, the curvature is very similar to this point. So whatever negative slope it has over here, this point 3 pi by 4 and this point 7 pi by 8, they are kind of
Sir, so differentiation of minus cos
sorry, this is 7 pi by 4. Okay, just a minute, guys. Okay. This is 7 pi by 4, and that should be my. Yeah. What was your point, beta?
so differentiation of minus cos 3 by pi by 4 with respect to x will be sine pi by 4, right?
Differentiation of sine x is cos x. Okay. Now the thing is, you have to substitute the value of x as whatever point where you want to find the slope of the tangent. You're getting the point now?
So it's already differentiated, that means.
It's already differentiated. The differentiation is this. This is the derivative of the function. Now I want to find the slope of the tangent at a particular point. So I have to find what? I have to find the value of the derivative at that particular point. So at pi by 3, for example, I want to find the slope of the tangent. So in the derivative, that is cos x, I have to substitute the value of x as what? I have to substitute it as pi by 3.
So what if it is minus sine x?
Minus,
Sine x.
the function is minus sine x.
Yes, so y is
Then the
equal.
derivative will become minus cos x. So the graph will change. Okay. So if you have the function, let's say, in fact, let's make it like this. I have the function, let's say minus 2 sine x. Okay. So the derivative of the function will become what? It will become minus 2 cos x. Okay. So if you observe the graph of the function now, that will be a function like this. The function shape would have changed. It will reach the value minus 2 at the point pi by 2. And it will reach the value plus 2 at the point 3 pi by 2. Okay, now let's say I want to find the slope of the tangent at some point like this. So this point is 3 pi by 4. So this function's slope of tangent at x equal to 3 pi by 4, that is nothing but the value of dy by dx or f prime x at x equal to 3 pi by 4. So that is minus 2 cos 3 pi by 4. So that will become minus 2 into minus 1 by root 2. So that will become plus root 2. Okay. So this will have a positive slope now, which you can see in the graph also. So this one slope is equal to plus 1.4. Understood now?
Yes, sir.
So any given function, like even if it is a more complicated function, like that earlier function I took, the sum of a sine term and a cos term, the slope of the tangent at any point we have to find in the same way. That first find the derivative of the function and then substitute the value of x in the derivative as whichever point we are finding the slope of tangent at.
So similarly, when y is equal to minus 2 cos x, so dy by dx will become 2 sine x.
2 sine x it will become. If you take y as, for example, cos x, then the derivative of the function is minus sine x by formula. Okay. So if it is minus 2 cos x, the derivative will become plus 2 sine x. Okay. So for example, if you compare the graph of cos x now, here the function itself is what? The function is cos x. Okay. So how does that function's graph look? It looks like this now. So now, for example, I want to draw tangent, let's say at this point. What should its slope be? So slope at pi by 2 should become the value of the derivative at pi by 2. So the derivative is this now. Okay, so it is minus sine pi by 2. That is minus 1. So you can see that this has a slope of minus 1. But similarly, if I were to draw the slope at, let's say, this point here, I'd see it will come out to be something positive. Let's say I've taken some point here, like again 7 pi by 4. Okay, so you can see that the slope at 7 pi by 4 will become minus sine 7 pi by 4. So that will be minus of minus sine pi by 4. So that will become plus 1 by root 2. Because for sine, you have the formula that sine 7 pi by 4 is minus of sine 2 pi minus 7 pi by 4. So that is But remember here the slope is minus sine. So minus of minus 1 by root 2. So the slope becomes plus 1 by root 2. Okay, so is this one also clear?
Yes, sir.
Okay. So like this, as you practice more questions and experience all this, it will become easier and easier for you to work these things out. Okay. Now, after the trigonometric functions in our basic formulae, there are two more types of functions that we deal with, which are important for us in physics particularly. One of them is the exponential function. So let's understand the exponential function itself, then we'll come to the derivative. So exponential function is given by this type of a formula, e raised power x, where e is a constant which is an irrational number like pi, and its approximate value is 2.7. So the graph of this exponential function, it looks like this. It has a shape like this. Okay. So you can see, for example, at x equal to 0, the value of y is e raised power 0, which is 1. Okay. At x equal to, for example, minus 1, the value of y would be e raised power minus 1, that is 1 by e. So that would be approximately 0.37 if you calculate it. So you can see that at minus 1, the value drops 0.37. At x equal to plus 1, on the other hand, the value of y is e raised power 1, which is approximately 2.7. So on the other side, you can see the value has increased. And it increases very rapidly as x increases. Whereas on this side, it decreases. Okay. So for example, at x, let's say minus of 1000, y will be equal to e raised power minus 1000, which is almost tending to 0. It's a very small number. So you can see it's tending to 0. Whereas on the positive side, if x tends to a very large number like 10 raised power 5 or something, y becomes e raised power 10 raised power 5, which is very large. It's tending to infinity. So as x becomes larger and larger, y increases to a larger and larger value here. Whereas on the other side, it's tending to 0 as x is tending to minus infinity. So that is the shape of the graph. Okay. So just take this down. Then we'll discuss about the derivative of this function, which has a very interesting property, which makes it a very unique and important function in physics applications. Okay, so let's look at the very interesting property that the exponential function has. And that property makes it important and interesting for us. And that is from the idea about the derivative of exponential function. So it turns out that the derivative of the exponential function is the function itself. Okay, so this is the unique property it has. This is the unique property of an exponential function, that the value of the derivative equals to the value of the function itself. Okay. So in terms of graph, let's understand what that means. Means that if we've drawn the graph of y is equal to e raised power x, then at any particular point x, the y coordinate of the function is e raised power x, but so is the slope of the tangent. So this slope is also equal to e raised power x. Okay. Or if we draw the tangent at a point like this, whatever the value of the function, the slope of the tangent is the same. So for example, at x equal to 1, the value of the y coordinate is also e. The slope is also equal to e. Okay. At x equal to 0, the value of the y coordinate is equal to e raised power 0 or 1. The slope is also equal to e raised power 0 or 1. So at any point x equal to a, let's say, the y coordinate is e raised power a, whereas the slope of the graph is also equal to e raised power b. So this and this are the same. So this is a very unique property that only one function in mathematics has, and that is the exponential function. And that is why it is important as a separate category of function. Okay, now let's come to the last of our function categories, and that is the what we call the natural log function. So the symbol that we use for this is y is equal to ln of x, where the symbol ln stands for natural log. Okay, and ln of x basically means log to the base e of x. Okay. So for this function, y is equal to natural log of x. For example, if x is equal to 0, that means, or rather if x is equal to 1, it means y is equal to 0. If x is equal to e, it means that y is equal to 1. If x is equal to, let's say, e raised power 100, it means y is equal to 100. If x is equal to, let's say, 1 by e, it means y is equal to -1. Because the inverse of this is that x is equal to e raised power y. Okay, that is the meaning of log. If I say log a to the base b is equal to c, it means that e is equal to b to the power c. So for example, if I say log to the base 10 of 0.1 is equal to -1, because so similarly, equal to 2, for example. So ln so this is the logarithmic function or the natural log function. Now the derivative of this function also makes it another unique type of function. Differentiation of ln x has a value of 1 by x. So one more important thing we should understand about this function is that y is undefined for x less than equal to 0. So y is defined only for positive values of x. Okay. This is somewhat like saying something like this. If y is equal to root x, you can see that y is undefined for negative values of x. Okay. Similarly, if I were to take the function 1 upon root x, then again y is undefined for x less than equal to 0, because here even division by 0 is not allowed. It's only defined for positive values of x. Here in the first one, y is only defined for non-negative values of x. Here y is defined only for positive values of x. So like that, the ln function or the natural log function also has the property that we can define values of y only for positive values of x. For non-positive values of x, y is not defined by this function. Okay, so this is our list of formulae for today. Okay, and this completes the essential formulae for differentiation. Okay. So just as a quick recap, let's quickly summarize all the formulae that we have seen. So the most fundamental formula was for the algebraic functions, that differentiation of x to any power n is given by this formula. Okay. Then after this came the 6 trigonometric functions. So if you just practice writing these formulae down a couple of times, you will see that you'll notice that there's a kind of symmetry to it and a pattern to it. So you can find it easier to remember them that way. And then finally, there are the two other functions, the exponential functions, its derivative is very easy to remember, and the natural log function, its derivative is 1 by x. So these are the essential formulae. Using these formulae along with the properties of differentiation will enable us to be able to differentiate any given function. So we've seen some of the properties also, and we'll see some more coming up next.
So,
Yes.
can you please again explain the natural log function part? I got disconnected over that time.
The natural log function, right, is defined as the logarithmic operation, but the base of the log is e, the exponential number. Okay. So as you know, the definition of log in maths, logarithm in maths, is that if we define logarithm of any number to a particular base, its value is such that this is the relationship between a, b, and c, right? So for example, if I want to define log of, let's say, 8 to the base 2, so what will the value be? I know that 8 is equal to 2 to the power 3. Therefore, log of 8 to the base 2 will be the number 3. Right? This is clear now?
Yes, sir.
Okay, now the standard base that we use in maths is 10 because of our decimal system. So standard base is 10. So when we generally use the term log, it means, without giving any specific base, it means log x to the base 10. Okay. So for example, log of, let's say, let's say log of 100 is how much? So we know that 100 is 10 to the power 2. So this implies that the standard base log of 100 should be equal to 2. Okay. So now, like that, we have what is called the natural log function. Okay. So the natural log function, it uses the value of the base as the exponential number. So ln x is nothing but log x to the base e. So now, for example, if I have x as, let's say, e to the power 5, so what is ln x? Okay, so ln x will be equal to 5 because we know that e raised power 5 is equal to, e raised power 5. This implies that ln x is equal to 5. Okay. Similarly, for example, if we have x is equal to e raised power minus 5, it means that this is minus 5.
Sir, so if we take log 8 to the base 2, which is 3, then derivative of ln x will be 1 by 8.
No, but that is not true for any log. No? It is only that derivative is only for natural log. You understanding the point? So we cannot take the base 2 and say its derivative is 1 by x. You understanding?
So the base has to be
If
8.
I have a function y is equal to log x to the base 2, then for this function the derivative is not equal to 1 by x. It's not equal to 1 by x. Okay. It's only when we take y is equal to ln x, that means log to the base e, only then we know that the derivative is given by 1 by x. Is it clear, beta?
So what is E? E is a constant?
E is that exponential number that we discussed about exponential function. Is the
Okay.
irrational constant approximately equal to 2.7, right?
Okay, so the irrational constant raised to some value is x.
Yes, yes. So when I say y is equal to ln x, it means the inverse of this is what? That x is equal to e raised power y. Okay. So if the value of y is 1, that means x should be how much? E. If the value of y is 1000, x should be e to the power 1000. If the value of x of y is -2, that means x should be e to the power -2 or 1 by e square. Is it clear now?
Yes, sir.
Yes, sir.
So then how to differentiate this y is equal to log x to the base 2?
Yeah, there is a way of converting the base. Okay, we will not get into that over here right now. Okay.
Okay, sir.
So if I have a function where y is log with some other base, not the natural base, then I have to convert that function to the natural base. And for that, there is a method in logarithms in maths that you will study called base conversion. So you can convert a function expressed with any base of log into any other base, including the exponential base. So you'll have to use that conversion factor and convert the log of some other base into log of natural base e, and then use the differentiation function. Okay. So that is not really required for us immediately. So I'm not getting into that. Okay. Don't want to confuse you with too many concepts. That's why. Yeah, Bhavika, coming to your doubt. The slope of at x equal to 0 on which graph? On the exponential graph you're talking
Yeah,
about?
yeah, exponential graph also.
So see, coming back to the exponential graph now. This was our exponential graph. So at x equal to 0, if we draw a tangent, how much slope it should have? It should have a slope of the value of e raised power 0. So if I draw a tangent here at this point, this is x equal to 0 point, then its slope will be how much? Its slope will be 1, because y equal to e raised power x, it has a rate of change dy by dx.
Okay, sir.
It has a dy by dx also equal to e raised power x. So therefore, at x equal to 0, dy by dx's value is e raised power 0, which is 1. So that is only the slope. You can understood now?
Yes, I understood.
So here only, if you put x equal to 0, you can see the y coordinate is also 1. The slope is also 1. Okay, so this is about the different formulae of differentiation. So as I said that this is the complete list of formulae that you'll have to keep in mind while doing differentiation based questions. But out of this also, for physics, the more important formulae for us are going to be these two. Obviously this one very important, and these two. Okay. The other four will be using more rarely in comparison to. Okay. Now let's talk about some more properties of differentiation. So continuing with more properties. Okay. So the next thing we'll see is the product rule in differentiation. So if the function is actually a product of two separate functions. So for example, suppose y is equal to x square into sine x. You can see it's a product of two functions. If you write the function fx as x square and the function gx as sine x, so you can see that the function y or the variable y is the product of these two individual functions. So in that case, how do we express the differentiation? So it is given by the product rule. It will be the derivative of the first function multiplied by the second function plus the first function multiplied by the derivative of the second function. You can write this in reverse order also. It can be f into g prime plus g into f prime also. It doesn't matter, okay, because it's after all a product. So here we are using that shorthand notation that f prime x is the derivative or the rate of change of fx. Okay. And g prime x is the rate of change or derivative of gx. So in this particular example now, if I want to find dy by dx, I'll use the product rule. So I'll say it is differentiation of the first function multiplied by the second function plus the first function multiplied by differentiation of the second function. And then I'll just use my formulae. So differentiation of x square is 2x and differentiation of sine x is cos x. So this becomes my derivative. This is dy by dx. Okay, so just write this down along with the example, and having written this down, you can try another example out. Y is equal to, let's say, e raised power x into square root of x. So find dy by dx and the slope of the tangent at x equal to 1. So just try out this question, people. Bhavika, I'll come to your question. Okay. For that, we have to use another property, okay, which is called the chain rule, which we are coming to next. Okay. By the end of today's lecture, you will learn that part also.
Okay, sir.
Okay, so anybody else tried out this question?
So can I rejoin the meeting? I'm not being able to send messages.
Yeah, you can rejoin. Kirti, try again. So it is a product of two functions where one function is the exponential and the second one is the square root function. So you can say here, you can treat it like y is equal to, in short form, we can just write f into g, where f is e raised power x and g is square root x. So what is f prime? It is derivative of e raised power x, which you know is e raised power x only. But what is g prime? it is derivative of square root x, which is 1 by 2 root x by the x to the power n rule. So now dy by dx should be f prime g plus f into g prime. So use this property. So see, we get this very interesting kind of function. So you can even take LCM and write it like this. Okay. So this should be our final answer. Okay. So we can also directly differentiate it like this, that differentiation of the product of these two functions is differentiation of the first function multiplied by the second function plus first function multiplied by the differentiation of the second function, and then just work these out. So this is e raised power x into root x plus e raised power x into 1 by 2 x to the power minus half. So that will only give us this. Okay. So of course our answer is correct at this stage also. We can just leave it this way also. So the slope of the tangent at x equal to 1 will be nothing but the value of dy by dx at x equal to 1. So that will become, as you can see, e to the power 1 upon 2 into 2 plus 1. So that is 3 by 2e. So approximately 3 by 2 into 2.7. So this is the slope that we are talking about. Okay, so very good. People have got this. So this is about the property of the product rule. Okay. Now let's move on to what is called the quotient rule. That is, if the function is actually a division or a quotient of two functions. So for example, if I have something like this, y is equal to x square upon x plus 1, okay, then how I would differentiate y with respect to x? So this is given by a rather lengthy formula. It is the denominator function into the derivative of the numerator minus the numerator into derivative of denominator divided by the denominator function whole squared. Okay. Or a shorthand way of writing this is that if it is some numerator divided by denominator, then the rate of change is denominator into prime of numerator minus numerator into prime of denominator divided by denominator square. Okay. So let's see how this works in this case. So this will be denominator multiplied by differentiation of the numerator minus numerator into differentiation of the denominator divided by the denominator whole square. So this should become x plus 1 into 2x minus x square into 1, because derivative of x plus 1 will be 1, and of course whole thing divided by x plus 1 whole square. So this will become x square, because 2x square minus x square plus 2x upon x plus 1 whole square. Now, of course, you can always try to play around with these type of formulae. So for example, if you want to differentiate y is equal to x to the power 4, one way is that you can directly use the formula. It is 4x cubed. Another way is that you could write this as x square into x square, for example, okay, and use the product rule. So you'll see this is x square into 2x plus, so that will become 4x cubed. Or another way is that you can also express this, for example, as, this will be a very stupid way of solving it, but it will just prove the point that this product and this quotient rule is correct. Okay. So it is denominator into differential of numerator minus numerator into differential of denominator divided by the denominator square. And you, when you work this out, you will see that this will give you exactly what it is expected to. Okay, so these kind of things can also be done. Or for example, you want to show that the differentiation of tan x is x square x. So find dy by dx by defining tan x equal to sin x by cos x, and using the quotient rule along with the standard derivative of sine x being cos x and the derivative of cos x being minus sine x. Okay, so just try out this example yourself.
So if you're using a direct formula for this problem, then it will be the formula which you have to use.
Yes, that's x square x. Okay, so now you can prove that what you got by that direct formula is also correct compared to what you get by the quotient rule. But then using the other formula, the derivative of sine is cos and cos is minus sine.
Yes.
Okay, so let's see this one. So treating this tan x like a quotient of sine and cos, and differentiated by writing denominator into differentiation of numerator minus numerator into differentiation of denominator divided by the denominator squared. Okay, so this would be the complete expression. So this would be cos x into cos x, okay, minus sin x into minus sin x divided by cos square x. So that is cos square x plus sin square x, which you know as an identity is equal to unity for all values of x. So it's 1 by cos square x, which by definition is sec square x. So that's one way to justify why the differentiation of tan x should be sec square x. Okay, so this is about the quotient rule. And now we come to the final property of differentiation, which is called the chain rule. So the chain rule is something that we use to differentiate what is called composite functions. So this is used to differentiate composite functions. So a composite function is of this type. It's basically a function operated on a function. So in symbolic language, we write it as f of gx. That means we have taken a function g, operated it on x first, and then on that we have operated the function f. So an example of a composite function is, let us say, y is equal to square root of 1 plus x square. So to get y, what we have done is on x, we have first operated the function 1 plus whole square. So we have got 1 plus x square. And then on that, we have operated the function square root. So we have got square root of 1 plus x square. Okay. So just make a note of this. I will continue. Okay, so you can see that if we are expressing y as f of gx, so first we are operating the function g, so we are getting gx, and then on that we are operating f, so we are getting f of gx, which is this. In this case, gx was the function 1 plus x square, so f of gx became the function square root of 1 plus, or square root of gx, you can say, which in the next step we can write as square root of 1 plus x square. Okay. Or another example of a composite function Suppose we have y is equal to sine square x. So what we have done is on sine, we have first on x, we have first operated sine. So we have got sine x. And then on that we have operated the function whole square. So we've got sine square x. So this is our f of x, let's say, or g of x, whatever. And then this is our f of gx. So when we have a composite function like this, the differentiation is done by application of what is called chain rule. Okay. So this chain rule application involves 3 steps, which you have to understand very carefully. Step number 1 is what we call the substitution step. So in this, what we do is we introduce or substitute a dummy variable. So for the function y is equal to f of gx, we will substitute a dummy variable z, which is, let's say, fx. So therefore, y becomes, gx, the inside one. So z should be equal to whatever we have operated f on. So that is our dummy variable z. So y in turn becomes what? It becomes f of z. So now you can see that both these equations together are giving the same information that this one is giving, but it's giving it in 2 steps. That x is operated by a function g to give me a dummy variable z, and then that dummy variable z is operated by another function f to give me the value of y. So y is a composite function. Y is a function of z, which in turn is a function of x. So that is the meaning of the term composite function. Okay. Then the second step is where the differentiation thing comes in. So that is called the chain rule step. So in the chain rule step, what we do is we express the rate of change of y with respect to x as the rate of change of y with respect to z multiplied by the rate of change of z with respect to x. So this is the statement of the chain rule. Okay, and in this now we are going to substitute these 2 things. And on substitution, the final step will give us, after resubstitution, the value of dy by dx. So from here you can see that this is differentiation of fz with respect to z multiplied by differentiation of gx. So that can be written as derivative of f multiplied by derivative of g. But the resubstitution thing is that z has to be resubstituted in terms of x. So that's where the resubstitution step comes in. It is f prime of gx multiplied with g prime x. So that becomes our final answer. Okay. So I'd like you to just go through this and write down these steps carefully. Then we'll do an example and it will be very easy to understand how to apply these steps. Okay, so let's understand quickly for an example. So we have y is equal to sine square x and we want to find dy by dx. So we understand that this is a composite function like we've seen above. Already understood that here. So to differentiate, step one that we use is the substitution step. So that in this case, we will substitute, we'll introduce the dummy variable z as sine x. Okay. So once we got the dummy, we can see that y is a very simple function of sine x, which is z square. So this is my first step, which is the substitution step. And the next step is the chain rule step. So the expression of the chain rule is very simple. So when I substitute here, dy by dx, rather dy by dz will be differentiation of the function z square, because just above we've seen this. Okay, and dz by dx will be differentiation of the function sine x. Okay, so this we are just substituting from here. So that, as you can see, will give us 2z into sine x. Okay, so this is the chain rule step. And the final step now, the resubstitution.
So 2z into cos x, no?
Oh, sorry, correct. The differentiation of sine x is cos x, very true. Yeah, so substitution, thanks, is resubstitution. So we will substitute or resubstitute z as sine x. So dy by dx, it become 2 sine x into cos x. So that is a derivative. So for example, for y equal to sine square x, I want to find the slope of tangent at x equal to pi by 6. So that will be dy by dx's value at x equal to pi by 6, which will be 2 sine pi by 6 cos pi by 6, or see that in this case it will be root 3 by 2. This will be the slope. Okay, so this is the method of application of chain rule. So chain rule again becomes very important for us because many a time we are dealing with composite functions. So you'll see some examples of this in your module also, and lots of examples in the exercises. Plus, I will be giving you another worksheet with examples of application of all the 3 properties we've learned today: the product rule, the quotient rule, as well as the chain rule for composite functions. Okay, and we will also do some more practice of these things in the next lecture. So with that, we conclude today's session. People, hope you have understood everything clearly. Okay, make sure to revise the notes carefully and let me know in case of any doubts and things. Okay. Also, again, to remind you, you have an additional doubt session for physics on Sunday, apart from your regular lectures this week. So try to attempt each and every question of the worksheets, okay, 1 and 2, as well as the 3rd worksheet I'll be sending you very soon, so that you can discuss any doubts, or if also go through your lecture notes once more carefully and note down if there are any points of confusion that you want to discuss. Then Sunday will be another opportunity to do that, both for vectors as well as calculus. Okay. So that's it for today's session, people. Wish you all the best.
Thank you, sir.
Thank you,
Bye,
sir.
sir.
Bye.
Bye.
Thank you, sir.
Thank you, sir.
Bye, sir. Thank
Hey,
you, sir.
Okay,
sir.
bye. Yes.
Sir, actually, I've sent one doubt you on WhatsApp long back ago. So can you check?
Yeah, I'll check. Okay, just can you type a message on top of it today, because it might have got lost in lots of messages.
Okay, sir, I
So
will.
just send me a reminder message on top of it now, so I'll respond to it immediately. Okay.
Okay, sir.
Okay.
And sir, you will be sending a recorded video today.
Yes, I will be sending the recorded video as well as this thing, the notes, right one?
Yes, sir.
Okay.
Thank you, sir. Bye, sir.
Okay. Bye.